CLion, a cross-platform IDE for C and C++. Download now.
Hi, everybody. Thank you for joining this session on Constexpr virtual CRTP comparison. A few words about myself. I'm a lecturer at the Academic College of Tel-Aviv-Yaffo and Tel Aviv University, co-organizer of the Core CPP conference and meetup group in Tel Aviv. I had many years in C++ programming, and I do touch code hands-on these days as well as a consultant. I do these days for the past years training and advising, and then such questions or such ideas come up from something that you see, and then you take offline and think about how things may or should be implemented. So the goals of the talk are to play with C++ in general, but specifically with comparison, to get to some hidden corners of the language and specifically with comparison and virtual functions, and to have fun with C++. So let's have the fun begin and call talk begin. Okay, so a short quiz. I'm ready for a quiz. Now, I will not count the votes or your score. You have to count your score yourself, but do that. So I will change the question from what should happen to what would happen, because should is something subjective in some cases. So the question is, in the following example, we have a person and a student. And quite naturally, the student inherits from person, let's assume publicly. And we call static assert. We can do static assert because let's assume that we have two Constexpr objects, as you can see on the slide. And let's assume that the comparison operator is also implemented as Constexpr, which we can do. And then the question is, when we try to compare a person to a student, and a student to a person, both in this case hold a single attribute, and let's assume that this single attribute is the thing that is being compared, and the single attribute is 124 in both, which is the ID. Okay, now it might be that student may have later additional fields, but let's assume that this is what we have. So the question is, what is the result, or what would be the result of this comparison? And the answers are both would pass, or the first one would pass, but the second one would fail. Both would fail. Or maybe one passes the first one and the other one, the second, would not compile. So I will let you think for a moment. It requires some thinking. What is the difference between the first one and the second one? Should be any difference in the result. And once you cast your vote, I will fill it, and I will share with you the actual result if we run this code. Okay, I feel that you have your vote casted. So the answer is that both would pass, and we have here an example where we have here, since student didn't add any field, we can take a look at the code and see why both would pass. So let's start with spaceship-operator in C++20. I'm opening the Compiler Explorer example that would be presented in a moment. And we can see that we have a person, and since student didn't add anything, then student didn't implement its own comparison because there was not a need for that. And now the question is, okay, we have a person and a student, and we have a student and a person, and eventually we go to the same, call the equality, the comparison operator of the base class here, okay? We inherit that in student, and both call this operator and pass. If we go back and see what happens if we do implement them, let's assume that we do implement them either in C+20 or in C+17. So let's assume that we implemented the equality operator, the comparison. So since we didn't implement the operator in student, both would call the one in the parent. And even if we call the student and check it against a person, since it would call the function that was inherited from the base class and the base class is getting a person, it will pass. Now, both in C+20 and 17, I run it here in both versions. So this was the first example. And in a way, I would say that, yeah, that is fine. I mean, I'm not sure that we want a comparison between a student and a person, but since they both share the exact same attributes, maybe in this example, this is okay. Okay, so let's go to the next question. And in the next question, the scenario is a bit different. Now we have a student which inherits from a person, but the student adds additional attribute. Let's assume that the student has also a student ID, which doesn't have to be the same as the ID. And it means that we do implement or we do default the comparison also for student, which means that student may use the comparison of person, but it should have its own comparison. And now the question is whether these static assert will pass, fail, both. Each one will have different results. What do you say? This is the time to cast your votes. And again, you cast it on your own system, write it down, put it in your own WhatsApp group with yourself or any other mean. So you can check. I mean, if you just remember, oh, this was my answer, usually we tend to say that the answer that was the correct one was what we had in our mind. Write it down so you can check yourself. And the actual answer is in C+20, both would pass, which is not good because in this case, the person is not a student. I mean, the student has additional attributes. Maybe in the previous example, we had some reservations, but eventually we can say, you know what, the student is a person, it has the exact same attributes. But in this case, they do not share the exact same attributes. Student add something. In C+17, by the way, when I say C+20, I mean in both cases, either you implemented equality or you rely on a default equality or default spaceship operator. And the reason that in C+20 both passes is that in C+20 there is a rule that if a certain call to comparison doesn't find a function, then the compiler tries to switch the arguments. So since when we call student comparison to person, there isn't any equality in student that takes person, because student is waiting for an argument of type student, we'll see the code, then the compiler says in C++20, you know what? I can switch the two because quality should allow switching the arguments. And then when I switch the two in C+20, the second line resembles the first one, or actually works as the first one. So in C+20, both passes. And the reason that both passes is because in person, the equality, the comparison operator is implemented to accept an argument of type person. And the student is a type of person. So it takes the student, it takes it uses that as a person, even though it is still a student because it takes the student by ref. And eventually it checks only the person arguments. In C+17 and before, the second line doesn't compile. And there's a reason the second line doesn't compile because student doesn't have a comparison that can take a person. Let's take a look at the code. So when I go to the C++ 20 spaceship operator or default operator, it doesn't. It is not really important whether I default the spaceship operator that brings in the default equality and less than, greater than, etc., or just default the equality. Anyhow, I have a default for person to person, and I have a default for student to student. Now, it would work correctly for person to person and student to student. I mean, there is value in the spaceship operator, but there is something that is not so, I would say, doesn't work correctly. I mean, it allows the comparison of a person to a student and a student to a person. And the first one goes to the person because the person is the calling object, and take student as a person ref, which is okay. I mean, this is how it works. The second one switches the arguments and go again to the first one. This was C++20. If I go back and I say, okay, and if we do implement the comparison, so if we implement the comparison by ourselves, then there is a difference between C++20 and C++17. If I'm in 17, then the second one wouldn't compile because student doesn't have its own the proper comparison that accepts the person. On the other hand, in 20, the rule of switching the arguments still obides, is still there. And since student can take person, the compiler says, you know what, I can switch the arguments. So this is the C++20. Both static asserts are okay, pass, and in 17, the second one doesn't compile. This was the second question. How are you with the results? Did you get all right till now? Let's go for the third one. So in the third one, student inherits publicly for person, okay, with additional data member, but now the comparison is not on concrete types. We're using a reference. So we have a pointer p person, which actually points to a student. So the pointer p person points to a student. Okay. So eventually, we try in a way to take a person p and a student, but the student seems to be for the compiler as a person. I mean, the static type here, if I ask in compile time, would be, oh, I'm a person ref. At runtime, I'm actually referring to a student. Okay, cast your votes. I mean, we have here a person ref to a person in both lines. What would be the result? And as you probably seen by now, it might be that it depends on the actual C++ standard that we're using, 17 or before and 20 on. Or maybe in this case, it's the same. Letting you to cast the votes. Let's reveal the results. So in this case, both pass. Um, and they shouldn't, in a way. I mean, this is a person. P is a person, and the pointer points to a student. So the student doesn't actually is not actually equal to the person, but both would pass because there isn't any virtual or dynamic behavior unless maybe we can implement the comparison operator as a virtual function, maybe. So since this is not a virtual function, we call the equality the comparison operator of person, and person to person, it only looks at the first attribute, and they are equal in both cases. In either in 17 or 20 or spaceship operator, whatever. You do the default, you implement, it's the same. Okay. This would be the last one before we dive into let's think how to maybe improve things. Okay, so the last one is we have quite a similar scenario of student and person, but we have now two students, student S1 and student S2. And we point to a student with a pointer to a person. So PTRP is a pointer to a person. And now we want to assert static assert wouldn't work here, even if those two students are Constexpr, because the compiler says, oh, it's a pointer. I don't know how to do that at compile time. Anyhow, we assert whether PTRP star deref on PTRP, I mean the reference to a person, because eventually it's a person which actually referred to a student, whether it is equal to S1. Now this one refers to S2, and S2 is not the same as S1. We can see that they are not the same. Okay, and here is the same thing. S1 and this one refers to S2. I mean, if I would ask what should be the result, maybe we would say that it should be false for both. But what would be the result? This is the question. And I'm letting you cast your votes. What do you think would happen? And the answer is both would pass in CS20. And in C+17, the second one would not compile because in the second one we have a student, and on the other side we have a person. I mean, the compile time type is a person ref, and student comparison accepts a student. Now, we do know that this is a student, but the compiler doesn't know. In C+20, it would pass because the compiler can switch. So it would switch. Even if we didn't implement anything special, I mean, either it is our implementation expecting a student, then it will call the person, expecting a person, or we used the default equality or default spaceship. So the links are there. You can follow them later on. I will share the presentation, but you can count on, yeah, this is the result. I mean, CS20 would pass both, even though they are not the same. And in CS17, the first one would pass, the second one would not compile. Let's summarize what we saw. Comparison between polymorphic types. We have a student and a person on the other side, or a person and a student. I would say that it should not compile, or if it does compile, let's assume that, oh, it compiles because student can take, student maybe can take a person. No, I would say that this one should maybe, oh, this one may compile, the second one, because person may take a student. So even if it compiles, I would say it should return false. This one should not compile, but if it compiles, then it should return false. The actual behavior is that in C+17, the first one actually doesn't compile, which is a good thing, I would say. But the second one compiles and may return true. Why it may return true? Because it would check the attributes of the first person against the attributes of the second student as a person, ignoring the fact that the second one, the argument, is a student. I almost said it's not a person. It is a person. It's ref to a person. And it may return true if the attributes of the first person and the second person are the same, even though there are additional attributes in student. In C++20, we try to improve things. And I would not say that this is an improvement. I mean, something that was, at least one of them didn't compile. Now it compiles, and it may return true. I mean, things are now symmetric. You're wrong in both cases. I would not say that this is an improvement. Now, one can say, you know what, it didn't work right to begin with. Yes, it didn't, because comparison, the default comparison or the comparison that we implement is usually non-polymorphic. And we have to think about, so what should we do? Okay, what about the second one? If we have a pointer or a reference, so I would say the same. If they are not the same type, it should either not compile. If I'm coming with student and providing a person is not a student, you can just, you can stop it at compilation time, at compile time. But if it does compile for some reason, then it should return false. They are not the same. The actual behavior is that in CS17, the first one would not compile, but the second one would, because a person can take a person, even though it points to a student, and it may return true. In 20, both would compile and both may return true. We saw that. That was the quiz. The third one we call here equality on a student, and another thing that at runtime might be a student. Now, C++, even if comparison is a virtual function, and it was not in the examples that we implemented and presented, even if the function is virtual, there isn't virtuality or dynamic dispatching according to the argument. So in any case, we are calling the equality of student, and the fact that the other one is a pointer to student, nobody knows that. I mean, the compiler says, okay, I see you as a person ref, and I'm not waiting for runtime to actually know which type are you. So there isn't any dynamic dispatching according to the argument. So either we have to implement something for that, or we should rely on, okay, this is how it works. The actual the actual behavior is that the first one would not compile in 17 because a student can't take a person, even though the person points to a student. Maybe we do want it to work if the person actually points to a student. And the second one may return true even if they are not the same type. And again, in 20, both would compile and both may return the wrong result. Which means that comparison between polymorphic types is utterly broken. From C++98, it's not a new thing. I mean, the new thing is that C++20 tried to improve things, and it did, but not for that domain, not for polymorphic comparison. I would say even that polymorphic comparison, things even became a bit worse because something that didn't compile before now compiles because of the switch of arguments and returns in some cases the wrong result. Or maybe I would say in all cases where the type is not the same type. But this is the case. And one can say, oh, so maybe you should not implement equality on a base class. You should always implement equality only on leaf classes, which comes with advice of implementing actual behavior only on leaves. I mean, base class should be abstract, but it would be the same. I mean, I can show you in this example that even if we have a BA student and an MA student, a bachelor and a master's, and we have a student pointer, the base class can still point. Let's assume that the base class is abstract. I can still call assert on both, and they can still both pass and call the wrong equality, okay? Because maybe I do want to implement equality on student, because student does have some attributes and I want to implement some things. Maybe I can say that equality at the base class should be protected. Might be. Okay, we may come up with another idea, but in this example, I will show you the example. We have leaf classes, and we actually call the equality on the leaf classes, and it will say that two are the same, even though PTRS points to S1, and the other one is S2, and S1 and S2 are different types. They're of different types. And eventually it goes to the default equality of student, which we do want. I mean, I do want this one. Why? Because I have attributes. Now one can say, so put it in the protected part. I can't. The default comparison C++20 cannot be protected. It should be in the public part. I can implement it, but if I do want to use the default, I should put it in the public. So eventually I have an issue also with leaf classes. And again, we are seeking maybe something that will solve that. And maybe we want something to behave polymorphic dynamically. So the problems is that it is non-symmetric or before C++20, but in 20 it is symmetric, but wrong in both cases. Two different types may be considered equal. That's bad. Default comparison is non-polymorphic. Can you add virtual? No, the default in C++20 cannot be virtual. You have to implement that if you want manually. So what should we do? So one thing that we can do is to avoid the different types comparison. I mean, if you know that there are different types, do not call equality comparison. Okay, how can you enforce that? How can I make sure that nobody does that? You should not call equality also with pointers or references pointing to different types, because I am not sure that the reference is referring to the type that I think it refers to. So in a way, the advice should be only use comparison on concrete types of the same type. Or maybe we can implement something better. What can it be? What can it be? What can it be? Oh, maybe it can be a Constexpr virtual CRTP comparison. Yes, that is what we are going to implement. A side note, the problem is not only for comparison. The problem is also first with other languages. It's not only C++. I mean, there is an issue with you want to do things with two types and it's complicated for some reasons. For example, maybe I will present the Java code. I mean, the Java code is not the best example because eventually in Java, you can implement that quite easily. But on the other end, it is quite easy to accidentally implement that wrongly. But even in C++, it's not only for assignment. It's also for, I said, it's not only for comparison. It's also for assignment. So a quick look at Java. So in Java, if you want to, you know that Compiler Explorer also supports Java. So here we are in Java. Okay, you see Java here. And I have the person and I have the equals function. In Java, equals is a function that is implemented in the base class object, which is the base of all classes in Java. Thus, when we implement equals and we override the equal of the base, we get an object as an argument. So inherently, the way to implement equals is to first check that the object that we got is the same type of ours. In C++, it is not the case, because when we get an argument in comparison, the signature would be that we expect an argument of the same type as ours. So we do not check that. I mean, if we would check that always, this is something that would solve the issue. But usually we do not. And in Java, this is the way to do that. Okay. There are other ways to do that which do not work the same, which are bug prone. I mean, you can see implementations in Java that check instance of, which is not the right way to do that. Okay, I will leave you maybe for the discussion in GatherTown later. If someone wants to speak about Java or C# or whatever, there is a way to do that correctly, and there are other ways which are used occasionally which are wrong. So Java has the issue as well, but it can be implemented correctly. Let's take a look at assignment. So I'm opening the assignment C++, back to C++. I'm sure that you heard about assignment of polymorphic types is problematic, right? We have a BA and an MA student. I have pointers. Eventually, when I call assignment on a person, this person actually points to a student. And I assign it to I assign to it a person of the same type, of another type, it doesn't really matter. I'm calling the assignment of person, which means that I'm assigning only the attributes that are part of person. That's an issue. I mean, most probably static analyzers would point at that assignment of and say you are assigning to a reference without knowing the type. There is an issue here. But you can see in the printout that S1 was assigned with S2, and S1 keeps the old value of the second attribute without taking it from S2. Okay, S1 takes the 122 from S2, but it doesn't take the 102. It stays with 101. There is an issue here also with assignment. But let's put assignment aside. I mean, we can solve it for assignment as well. We can discuss that. But let's go back to our problem was with comparison. And the problem started with comparison because C++ 20 tried to solve things. And yeah, it did improve things, but in other domains, I mean, I don't have to implement equality if it is trivial, but it doesn't behave polymorphically. So back to comparison. Let's implement a virtual comparison, okay? We want to start from here. We want to start from, we have a person, we have a student, maybe we have a master's student, which inherits from student. Just we want a few levels, so it would be a bit complicated, okay? And the current comparison doesn't work well. We know that, okay? Things that should uh, um, pass, like, yeah, they are not the same. This should pass, they are not the same, actually fail. And things that should fail actually pass. So we have to fix these. Let's fix them. I will just jump. The idea was maybe we will do some live coding, but I will skip that to have time to discuss all the different alternatives that I want to discuss. So let's first, I will just jump to a possible solution. Let's try to have the comparison operator virtual. I mean, we can have virtual operators. So this is going to be our first trial, okay? So we try to add the virtual function, the virtual keyword. And in C++20, by the way, virtual functions can still be Constexpr. How come? If the function is being called at compile time without any dynamic dispatching, then the compiler says, okay, I know the concrete type, I know what you're calling, and I will do that in compile time as a Constexpr. So it can be Constexpr and still be virtual. This is since C++20, okay? So eventually I can call static assert on things. The issue is that once you say virtual here, then and I can actually try to put virtual on a default operator. It is okay with that. But then the virtual function goes down as, I mean, it is being inherited by student. So in student, we now have two comparison operators. One that takes person, that was inherited from the parent, and another one that takes student. But the one that takes students hides the virtual one that was inherited from the parent. This is the hiding rules. Once I have a function with the same name as a function that I inherit from the base, then the function that is inherited from the base is being hidden. The reason is to avoid erroneous or the call that you didn't want to call. So this one hides the base class. Now, once it is being hidden, then I don't have the implementation for the virtual function. So I have here issues that the thing doesn't compile. Okay, we can play with that. We can make it a bit better, maybe. So let's try to maybe implement that and maybe implement that in the derived class, or using to bring it back to the derived class. So first attempt for another solution. So we have a person, we have a student, and we have a master's student. And now we say, you know what? Let's implement the equality in the base class, okay? And let's say that it is not virtual now, okay? And we actually check that we have the same type. I mean, if you go here and we do not show the same type, then it's false. Quite similar to the way that we saw in Java, okay? And in other languages. It makes sense. We have to be the same type to be equal. And then in the equal of student, we check again that we're the same type, and then we call the parent. The problem is that once we call the parent will check again that we're the same type. Type ID of this. Oh, but type ID of this would check dynamically that we're the same type. We just, maybe it's not so efficient, but I'm not checking that you're a person. I'm checking that you share the same type. Okay, so this should be fine. And then I'm checking the ID, and then the same thing for the master's student. I mean, it makes sense. I'm checking, are you the same type? Okay, let's now check the other attributes. So everything seems to be okay, but still, when we come to dynamic dispatching, dynamic behavior, we will have issues. I mean, you have to implement virtual functions to make it work. Otherwise, if you have a pointer to a person, then the pointer to person would call the person directly, and it would only check the ID. I mean, the type ID may work correctly because maybe the person is a student and the other side is also a student, and we're fine. But then it would not check the attributes of student because we didn't call the student function, we call the person function. So in order to make sure that we will call the student function and not the person function, even if the reference is a person, we need the function to be virtual. So we go back to, okay, let's think about a virtual function. So we need both a virtual function and something that would also check for type ID. Okay, let's go for a second attempt. So our second attempt is, we have now equality for person. And the equality for person eventually calls an equal function, which is the virtual function. The reason that we hide the virtual function in the protected is both because we do not want the comparison to be virtual. It doesn't work even if we implement that. We have to call our type, which means if you're a person, you will reach this one. But then when you call equal, you will reach the equal of student if you are actually a student. An equal of student will check all the attributes of student. So this is the part that checks for equality in a polymorphic way. And it goes well with the advice of hiding your virtual functions in the protected or in the private and exposing only non-virtual functions. There is some kind of a guideline like that. Not necessarily being adopted by everyone, but it has some value. So the comparison is non-virtual, but we have an equal function. Okay, let's see how it is implemented in student. So student doesn't have to implement the equality because we can say, you know what? You can always come to the equality of person, which first check that you share the same type. This is checked dynamically. Of course, it is checked dynamically only if you have a virtual table, but you do have a virtual table. So once you have a virtual table, type ID is being checked at runtime, and it checks whether we share the same type ID. And it might be that I'm a student and you are a student. That is okay. And then we call equal, and we will call equal of student because equal is a virtual function. So student implements its own equal, um, and for that, student needs to call the equal of the parent because we reached equal of student skipping the check of the attributes of person. And then student says, oh, when we call equal, before checking or together with checking my ID, I want you also to check the attributes of person itself. Oh, you will reach the equal of the parent. Same thing with master student. Master student says, okay, I'm implementing only equal. I'm calling student equal. This is my parent, which will call person equal also. And I'm checking only my attributes. And now it works for polymorphic type, for references, for different, and I mean, I check here the different scenarios that we had in the quiz. Now, it seems nice. It seems to work. And I would stop here unless I would say there is something in a way that is being um, duplicated, not too much, but a bit duplicated in the different derived classes. In this case, in student and master's student. And the thing that is being duplicated, I mean, it's very small, but I want to take this small thing that is being duplicated and bring it to a base class. And the thing that is being duplicated is the fact that I need to call equal of the base. And the problem here, it's a very small problem, but the problem is that it might be that a certain new derived class that would want to implement equal will implement equal by comparing its own attributes and forgetting to call the parent. So the way I would call it design by contract, or when you implement a derived class, you don't have any other choice because the base class already implemented that in a way that your equal goes through checking quality of the parent. I want something like that. Okay. Now to achieve that, it means that I would not implement equal. Equal will be implemented in the base class in a way. And the way that equal should be implemented in the base class is that it would say, okay, I want to first parent is equal, and then I want to check your attributes, something like that. But checking your attributes is yours. So I leave you only with checking your attribute. This is what I want to achieve. Now, a small point here is that in the implementation that we saw, we use Constexpr on a virtual function. The virtual function was equal. We want it to be Constexpr so we can do static assert whenever the types are known at compile time, and use assert in case we are using references. But in order to have a Constexpr virtual function that actually is using type ID, and we do use type ID somewhere here. Oh, we use type ID not in the virtual function. We use type ID in another Constexpr function here. We want a Constexpr function with type ID. In C plus 20, it doesn't compile. Why? Because type ID in 20 was not Constexpr. So we compile it here with 23. So another thing that we would want to achieve, and we'll find it in a moment, is we want also to have a C++ 20 version that is Constexpr. So we would have to implement our own type ID. We will do that in a moment. Okay. So first, let's start with, we want equality in a way, everything that can be implemented in the parent to be in the parent, to be in the base class. Let's do that. Okay. Remember, we have a person. We have a student, and we have a master student. But we want to add now another class, a new one. Let's call it a comparable class. And comparable will, in a way, inject behavior to a class. So comparable is saying, okay, I may be, or I'm going to inherit from someone. You will tell me who is my base class. So there is a base, okay? Maybe there is also a base ancestor. Maybe I'm inheriting from student, but the base ancestor, the one that started the hierarchy, is person. So I need to know two things. Who is my base? And who is the base ancestor, the one that started the hierarchy? Now, it might be that you started the hierarchy, my parent. So this has a default which says, oh, you only have a base. The base doesn't have any additional base. Okay, so don't provide this one, and the ancestor would be the base. Why do I need that? We'll see in a moment. Comparable inherits from base. And then comparable says, okay, give me the attributes for the constructor, because I need the constructor, and I will forward that. I will forward all the arguments to my base, because I need arguments for my base, maybe. Okay, now I do have an equal implementation, which is Constexpr, and the equal implementation is saying, give me the other as a reference, but I want the other as a reference, not as a reference of type base ancestor. I'm implementing here quite similar to the way Java does that, an equal that is expecting a base ancestor, is expecting, oh, you're implementing an equal for student, but we will expect the person on the other side. Why? In order to have the same virtual function, I mean, the virtual function must have the same signature. So once you have a virtual function in the base, the signature must be the same in the derived. And if the base is expecting a person, then the derived must expect a person as well. So we will be expecting a person. But then since this function is going to be used in student or in master's student, then the first thing is, and you see, we get an actual type as a template argument as well. It is going to CRTP, curiously recurring template pattern. The derived one will say, who am I? Who is the actual type that we are implementing or using this comparable for? So the actual type is the one that we want to cast to. The other should be of the same type. Now, we don't check here. I mean, this static cast is very dangerous. How can you static cast to something that you're not sure is the actual type? Well, somebody told me in the template, can you rely on that? Well, I'm relying on that because the one that would call equal will check before if they are share the same type. And if they do not share the same type, there will be a false before calling equal. So when you will call equal, which is a protected function, you will know already that they are the same type. Okay, so I can static cast to the actual type, and then I call base equal. I'm coming back up to my base. Base, can you do your equal? And then I call self equal. Okay, and self equal is virtual. And I also provide back base self equal from my base, because maybe my base implemented self equal, so I don't want to hide it. I want also to get back the self equal of my base. Otherwise, I may get compilation error of hiding a function. Okay, let's go to person. Person implements equal. Person implements equality, which is the public function that we expose. And in equality, we check type ID and then we call equal, quite similar to what we did before. Person implements equal. In equal, it calls self equal, because in person we only have self equal, and self equal is being implemented. Person is not derived, is not inheriting from any other class. Now we have student. Student is a comparable. Student is comparable with my actual type is student. My base is person. Now, once I inherit from this one, I get the equals function from comparable. And the equals function did the right work. Eventually, it will call self-equal, which is the only thing that they have to implement. Same thing goes with master student. But master students also have to provide the base ancestor. This is my ancestor. Why? Because you need to use the ancestor for the signature of the equal function that expects a reference to the ancestor. Otherwise, it's not the same virtual function. Okay, so I have the same virtual function for equals implemented in my base that would do part of the job, but then would call self-equal. And eventually, the derived classes only have to implement self-equal, which is nice, I would say. I mean, you don't have to think about, oh, I have to call my parent. No, it is being done in the comparable base class. So let's go back to comparable. Comparable is a base class being implemented with templates using the CRTP, curiously recurring template pattern idea. And the idea is that some of the implementation is being done in the base, but it is a base implemented or being generated specifically for me by the compiler. We may discuss that in Gather Town after we finish. Maybe we'll have questions on that. I'm coming back to the presentation. Remember that C++ didn't have that? So didn't have type ID. So in C++, I will do it quite quickly. It's not the most important part of the talk. We can implement our own type ID. And we can make, even in C++, our own type ID be Constexpr. So in some cases, we implement our own type ID because we run or we compile in an environment that doesn't have RTTI, runtime type information, and we still want something like type ID. So we implement something like get identity. Now, what would be the identity of two types which are the same? Well, a very simple way to achieve that is to have in each type, let's have it here. I added it directly into comparable, but we can add it maybe to another interface, might be even smarter. I have a Constexpr static field identity. Now, since this is a Constexpr static, I can give it a value just here. Like I can initialize it. I don't have to instantiate it in the CPP. It's a Constexpr static, but it has a unique address which is shared across all instances of the same type. So my type is based on the address of this identity, but another one with another actual type would have another static for this one because it's not the same class. So if I inherit from another one, each one that is using different arguments for the template would have another static field with a different address. So the address of this field is my ID. Okay, this is the idea, and we can separate it maybe even better to a different interface. That was a short view, a glimpse into how to implement your own type ID, and the code is here. You can go there afterwards. I still have a few words on. We can do it with multiple bases and with virtual bases. I will not go through that. While implementing the idea of CRTP with multiple bases with a virtual Constexpr function, it's the edge. It's the edge of using C++23 on features that are new to compilers, and bugs were opened both on GCC and Clang. So these are pointers to bugs opened on Clang and GCC on trying to use the most new feature in C++23, like a Constexpr virtual function with type ID inside a class with multiple bases. Something eventually, in some cases, doesn't work because compiler bug. But the idea works, and eventually there is something working here. I will not go through that. There must be another way. I mean, that was nice, CRTP, but maybe we can do it a bit simpler. Well, I would say that no, we cannot do it a bit simpler. We can do it in another way, which would not be, I would argue, simpler. Other alternatives. So there is an alternative of implementing templated equality that does the work for all types, saying, okay, the first thing that there's a templated equality I need to check is that you share the same type. And then I call equal. And in a way, it would achieve something similar to the thing that we saw in Java, saying, oh, maybe there is something which is generic, checking that you have the same type, and then the rest can be done by you. I will just jump to the code to show you the idea. So the idea would be to have some kind of a generic equal function, in our case, saying, I'm checking type ID, and then I'm calling your equal. And now we can implement equal. Now, for person, we just have to get the equal. For the others, what we want is to make sure that when you call equal, you reach the right one. Now, a person here is, it should have been a pure virtual or abstract. Anyhow, the idea is that the generic thing might be a global function. Okay, it doesn't really change anything significant. Going back to the presentation, there is another option of the same thing which doesn't work so well. The other one actually works. And there is another way. Another way is to make equality protected in the base class. So let's take a look at that one. We can say, you know what? Let's have only a student and a person. Student puts equality in the protected, which means you can't call it. So once you want to call something, you must call it through the derived class. Okay, but it means that we actually block all the cases of the other type is a reference to a base, which we do not support it. You come to with a reference to a base, even if the reference to the base actually points to your type, we would not get it. While in the previous implementations, we did support that. So eventually, we just want our code to be less bug prone. Let's block something which is not supported, which we achieve here. Maybe we can have something with reflections in C++26, which would be added on top of a class saying, okay, or a wrapper to a class saying, I want this class with equality, but equality not the default one that is not polymorphic. I want a polymorphic equality that checks the actual type, etc. And then would generate the code or use the code that we just implemented. Let's summarize. We will do it quite quick. Comparison is broken. If you if you avoid using comparison between different types, or fine. But how can you avoid it unless you implement something in the protected, or you do not implement comparison at all? But once you implement comparison in the base class, the derived one can use it. There is an option for polymorphic comparison. We implemented that. If you want to make it Constexpr, you can, even in C++20. Virtual functions can be Constexpr. If you want type ID to be Constexpr, that starts in C++23, but you can implement your type ID function even in C++20 to be Constexpr. Other options that we discussed is a global templated function. We had a very quick look at that implementation, or to block equality on the base class. There are some additional links for what is the right way to overload operator equality. And I think this is what I wanted to achieve in this talk. I think that we will discuss it further in the other time. So thank you all.